Alright, what homework did you just turn in? Homework 7? Is it 7? Yeah. I haven't posted solutions yet. I'm still waiting on one more late submission from somebody, so I think he's going to get that to me on Tuesday, so I'll post up solutions after that, I guess Tuesday night or Wednesday morning. The homework I just assigned is only 3 problems, but that's because I thought at least one of the problems was pretty difficult. If you haven't looked at the PDF I posted that has the problems on it, I also included some notes there, some hints, some suggestions as to how to proceed. But we can talk more about them on Wednesday, I guess, if you haven't looked at them yet. So we'll do that Wednesday's class. Today, we'll move on. 6.5 is actually a really short section. We should be able to do this all today, and maybe then some, which is area in hyperbolic geometry. So the big question is how should we define the area of polygons, right? So here's the question, and what should the area of a polygon, or we'll just say a region, I guess really we're sticking to just polygons here. We're not getting that fancy with it, curvilinear regions or anything. So what should the area of a polygon be defined to be? And obviously we want to sort of maintain, at least aesthetically, some sort of intuitive idea of the area of a region sort of is how much space it takes up, right? But how do we do this in Euclidean geometry? Well, the area in Euclidean geometry, you kind of think of how many unit squares you can fit into your region or something like that, right? What's the big problem with thinking about unit squares in hyperbolic geometry?
There's no square.
There are no squares, right? Rectangles don't exist. A square is a rectangle. So unit squares don't exist in hyperbolic geometry. So we can't really do that. But let's at least look at some properties it has to satisfy first. Right? So it must. So whatever we do, our definition of area must satisfy certain properties. Alright, so you can think of these as sort of conditions that meet the definition of area. We take some sort of a universal definition for what area should be, and then it has to meet these properties. But they're actually postulates of SMSG. They are, I believe, the area postulates are 16 through 20. So we want to satisfy these postulates. The first one says every polygonal region has one and only one area. So this is SMSG. I said 16 through 20. I'm at 17 through 20. 16 is the Euclidean parallel postulate. So that makes sense, right? You want to define a region with an area? Well, it should have exactly one area. You shouldn't be able to point to the same region and say, this is area 5 and 6, right? It's got exactly one area, and every region can be defined in area. All right, so what about this? 2 congruent triangles have equal areas. This is in fact postulated. This is SMSG number 18. So this is really important, and this naturally extends. This says that all congruent polygons will have equal areas. So this is something else you want. If two triangles or polygons, if they're congruent, you certainly want them to have the same area, right? They're the same shape, they're just positioned differently in space, but you want them to have the same area because they're the same in all other aspects. And 3, if a polygonal region is partitioned into a pair of subregions, the area of the region will equal the sum of the areas of the two subregions. And this is SMSG number 19. I wonder if this temperature control is actually working. All right, so we want additivity on the area. Whatever we define area to be, we should have this additive property that says if you take a polygonal region, slice it into 2 pieces, you can recover the area of the original piece by adding the areas of the 2 smaller pieces you sliced it into. And so we already have something that we've been looking at that has exactly these properties. It's defects. Every polygonal region has exactly one defect. Congruent triangles have equal defects. And if you take a polygonal region and slice it into 2 pieces, you can recover the defect of the original by adding the defects of the 2 smaller pieces you slice it into. So this is essentially what we're going to go with. Instead of we have this problem with squares not existing. We don't have unit squares. We can think of piecing into our polygons to figure out its area. We're essentially going to go with triangles instead. We're going to ask ourselves, how many triangles can we fit in to get area? And that leads to defects. Sorry, can I erase this? Okay. All right, so the idea is squares don't exist, so we use triangles instead. And that is, we can assign to each triangle a unique number, its defect. All right, so what I'm getting at here is 2 polygonal regions then. 2 polygonal regions, they should have the same area if and only if they are equivalent. bit of a non sequitur from what came before. This is just sort of a side statement, I guess. What I'm writing doesn't follow immediately from it. But does that feel okay to you? Right? Remember what equivalence means. Equivalence means we can slice two polygons are equivalent if we can slice them up in such a way into a bunch of triangles where these triangles are pairwise congruent. Right? So if you can slice two polygonal regions into a bunch of triangles and rearrange the triangles for one so that it reforms into the second polygon, then they certainly should have the same area. So I think this is a reasonable definition. And here's the really important catch, and this is your homework. This is the last problem in homework 8. Two polygonal regions are equivalent if and only if they have the same defect. So, I was going to say something about that. But yeah, we've already proven this for triangles. We've proven that two triangles are equivalent if and only if they have the same defect. Your homework is just to generalize that to polygons in general. Again, if you read through the notes I posted, formal proof of that is actually pretty tricky. If you want to accept that as sort of a challenge, feel free to try and write a proof. But just a loose, informal justification of why it's true is fine there. But anyway, so because we have this, we want them to have the same area if and only if they're equivalent. We know equivalent really means same defect. This is the definition we're going to make. We're going to define the area of a polygonal region to essentially be its defect. So moreover, if we simply define the area to be the defect, this satisfies the three properties we needed. SMSG numbers 17 through 19. Or properties 1 through 3 that we just listed. We'll verify this in a second, but shouldn't be too hard to convince yourself of that. There's one problem. What's a big problem here when I'm talking about the defect of a polygon? Well, how am I measuring the defect? Right, what units am I using? Am I using degrees? Am I using radians? Am I using some other angle measure? And the answer is it doesn't matter, just be consistent. So once you decide on one measurement, one scale to use that scale forever. So one problem, should we measure defect? Should we measure defects in degrees, radians, something else? And the solution, like I said, doesn't really matter. Solution doesn't matter, just be consistent. What I mean is once you've made this choice in your model, you stick with that choice forever. does is give you the size of the units, right? It's exactly the same as in Euclidean geometry in the real world. You just have to define your unit size. Once we decide what the length of 1 foot is going to be, then you have square feet, right? Once you decide the length of a meter, then you have square meters. Once you decide what angle measure you're going to go with, that gives you your sort of scale in hyperbolic geometry. So we'll take this as our definition, show it satisfies the 3 properties of area, and then we've defined a reasonable notion of area. So our definition. The area, which will denote A of P, for a polygon P in the hyperbolic plane is area of P is it's fine to think of it as just the defect, but remember defects can be scaled to whatever units you want. So people usually define this as K times the defect, where K is just any scaling factor that you choose for your space. Right? So K is any fixed, so it's fixed. Once you choose it, you've chosen it forever. Any fixed positive constant. Right, so this is sort of, just think of this as a measurement scale. And D of P is, of course, the defect. All right, so this clearly satisfies, I'm running out of space, we'll just do it over here. This clearly satisfies SMSG number 17. All right, 17 was our first property, said every polygonal region should have exactly one area defined to it. So for every polygonal region, there's exactly one defect associated with it. And satisfies SMSG number 18, which said congruent triangles should have the same area. Well, congruent triangles have the same defect, so by this definition, they have the same area. The book formally states both these as theorems at this point. It says, that every polygon has exactly one area. Congruent triangles have the same area, so if you want to sort of think of these as theorems. But they're obviously satisfied. But what about number 19? Let's just check the additivity real quick. We know it works, but let's just formally check this. So is SMSG number 19 satisfied? I don't want to say formally, we're just going to sort of intuitively convince ourselves that it works. But suppose I take a polygonal region. All right, so this is my polygonal region P. And I want to show that if I slice it into 2 pieces, I can add up the area of the 2 pieces to recover the area of the whole region. So we'll slice this into 2 pieces. We call it R1 and R2. So what do we want to do? We want to show that the area of P is the area of R1 plus the area of R2. Let me put these labels, sorry if you've already done this in your notice, but let's just put these labels outside. Well, let's compute these things. Area of R1 plus area of R2. What's that going to be? That's going to be K times the defect of R1 plus K times the defect of R2. Whatever we chose K to be, it's fixed. And how can I get the defect of this region? Well, I could slice this into a bunch of triangles and add up the defects of all of those triangles, right? Because we have additivity on defects. So how about I call this triangle A1, A2, and A3. And I'll slice this into more triangles. Call this triangle, I don't have much space here, B1, B2, and B3. So then this will be K times the defect of A1 plus the defect of A2 plus the defect of A3 plus K times the defect of B1 plus the defect of B2 plus the defect of B3. Or factoring out this K, this will be K times all these defects. Getting really lazy there with the dots, but yeah. Are you content so far? And if I want an area of these two regions, well, that's the sum of K times their defects. How do you get the defects of a polygonal region? Well, you could think of slicing into a bunch of triangles and then adding up the defects of those triangles. And this expression that I have down there, my last expression, K times the defects of all of the triangles, well, if I add the defects of all of the triangles, I've recovered the defect of P. Right, so this is K times the defect of P. And that is the definition of the area of P. Any questions? All right, so we haven't proven this in general. We haven't written down a formal proof of this fact in general. But I mean, this is how you should be thinking of this in your mind. This is why this works. When you slice it, it's because, you know, if you want the defect of this side, we'll slice it into a bunch of triangles. If you want the defect of this side, slice it into a bunch of triangles. Add them all up, and you recover the defect of the whole thing. All right, so we have this definition of area. It meets the properties that we need area to have. So we're going to go with it. Whether it seems natural to you or not, it meets the required properties. So this is how we'll define area. And we have a couple of theorems here, actually just one, which is if triangle ABC is a hyperbolic triangle, then the area of triangle ABC is less than k times 180 degrees. Where we're using degrees as the unit of angular measure. This is actually somewhat non-typical. Most people will just take k to be 1, obviously, and they will use radians, in which case you'd have that the area of a triangle, the maximum area of a triangle, where it's bounded by pi, right? How do we prove this? Well, this should be pretty simple. The defect, or how about the angle sum of the triangle is between 0 and 180. So that, of course, means the defect is between 0 and 180. Which of course means that the area of a triangle, multiply both sides by k, k is a positive constant. So k times the defect is less than or equal to k times 180, which means the area of the triangle is less than k times 180. This is, again, a really surprising result, right? This is, again, one of these types of reasons why Security looked at this stuff and said, this must be inconsistent. How can I have triangles where I'm allowed to have arbitrarily long sides, right? Our triangles can have arbitrarily long sides, and yet I have a bound on how much area they can encompass, right? That's really strange. Right, so this is a strange result, but interesting. Right, it says that there is an upper bound on the area of a triangle. Despite having arbitrarily long sides. And in fact, I think this is the last one we'll have in this class, but you can add this to our TFAE list, the following are equivalent to Euclid's fifth postulate. You can actually show that the statement that there is no upper bound on the area of a triangle is equivalent to Euclid's fifth postulate. So you can show that, I'm not sure our textbook mentioned this actually, but you can show that Euclid's fifth postulate is equivalent to the statement there is no upper bound on the area of triangles. And this is because, and we're not going to get into all these properties in hyperbolic geometry, we won't spend too much time with it, but triangles in hyperbolic geometry have this property they're called thin. All right, and even though we usually, in our models, we're going to have, a right triangle in hyperbolic geometry, in our models, we're going to draw them, something like this. Here's a nice right angle. Here's two straight-looking Euclidean lines that happen to be hyperbolically straight in this case. But and then we'll have this curvilinear side over here. The reason there's an upper bound on the area of triangles is they don't really look like this. They look like this in our models, but if you go into hyperbolic geometry, a right triangle like this actually looks more like this. All right, they are super, super thin. So you can make these sides very, very, very large and add hardly no extra area. Right? When you go off asymptotically, you're not adding any areas. You go this way or this way. So this is why there's this upper bound, is because triangles actually look bizarre. They're very, very, very thin. So one more quick corollary is, of course, we can generalize this corollary to n-gons, and if we have an upper bound on area of triangles, we have areas on upper bounds of n-gons, or upper bounds on area of n-gons. Corollary, the maximum area of an n-gon is k times n minus 2 times 180 degrees. And I'm actually being a little bit loose in my statement there. This can never actually be attained, right? It's an upper bound for the area, so it's not actually the maximum, because you can never get there, but it's an upper bound. So an upper bound for the area, maybe we should have said. Unless you allow yourself to think about ideal n-gons. If I never talk about ideal n-gons, remind me, because they're interesting. So yeah, we have this. As promised, area, very short section. But now that we've gone through all that defect stuff, we've got additivity on defects, we've studied defects, as long as we define area to be defects, that's really all there is to the section. We'll move on to 6.6. A model for hyperbolic geometry. we've already seen one model. We've seen this upper half plane model. That's not actually what I want to look at here, but breaking my chalk today. But we've proven lots of strange results, right? We'll come back full circle. We've proven lots of strange results. In hyperbolic geometry, which sort of begs the natural question of, are we doing anything useful here? Is our axiomatic system even consistent, right? So which begs the question, is this axiomatic system, is it even consistent? And as we know, going way back to the beginning of the semester, you prove consistency of an axiomatic system by building a model, either a concrete one or to prove absolute consistency, or an abstract one to prove relative consistency. So we can show consistency by building a model. Several models exist. One is one we've already seen, the upper half plane model. Some people throw Poincaré's name in there to give him a little bit of acknowledgement. So we'll call it the Poincaré's upper half plane model. This is the one we've talked about already because it's very easy to talk about, very easy to describe. And if you ever want to sort of think about what's happening in hyperbolic geometry or possible counterexamples or whatnot, it's a quick and easy one to go with. But by far the most popular is not his upper half plane model. It's actually what you get. So it's the upper half plane, right? Imagine taking this boundary, the boundary of the upper half plane, and curving it. Curve it even more, curve it even more. What do you get if you curve it around on itself? You'll get a disk. All right, so instead of having an upper half plane, we've got Poincaré's disk model. Poincaré's disk model. That's the American spelling of disk, right?
I was about to say, is it a C or a K?
I think British is C and American is K. I don't know which one's which. I use them interchangeably. But Poincaré's disk model. And there's one more that we'll talk about if we have time. I don't think our textbook mentions it, but it's the Beltrami-Klein model. Also a disk, but with different lines. There are others. I mentioned a few weeks ago that consistency was originally established by this guy, Beltrami, building a model. I believe it was 1868 he did this. And his model was none of these. It was built on what's called a pseudosphere. It was strange and not nice to use. But later on, people came along and then built these better models. These are, of course, 2D models, meaning they're models of two-dimensional hyperbolic geometry. You can extend this to 3 dimensions. You need different models for that. So we're just talking about 2D models for 2D geometry. And what we're going to spend most of our time looking at is the disk model, Poincaré's disk model. So what do I have to do? I have to tell you what our lines are, what our undefined terms are, and so on. So here's our model. What's the underlying space? Underlying space is a disk. An open unit disk. Usually denoted by a boldface D, and it would be all points x and y such that x squared plus y squared less than 1. All right, so this is what we're going to work with. This, of course, tells me it's all points, all coordinates in the plane x and y, whose distance from the origin is less than 1, so of course we get an open unit disk. Open meaning the boundary is not included. If you, I don't know how much topology you guys have had, but that's all I mean here. For the record though, forevermore when I draw pictures, I'm not going to dash out the boundary. Just keep in mind the boundary is not actually included. It plays a role if it's out there at infinity. But forevermore when I draw the disk, I'm just going to draw a solid circle. All right? But the boundary is not included. What are our points going to be? Point is just a point in the disk. And our lines come in 2 different types. One, we've got diameters of the disk. Diameter of the disk, D. Once again, the endpoints are not included, right? Their endpoints are out there on the boundary, which are not part of the model, so no endpoints. Or 2, if C prime is a circle that is orthogonal to the boundary of the disk, are you guys comfortable with this notation? Have you used this before? It's basically the partial derivative symbol, but in topology it means the boundary of the disk. So here I have the disk, and the boundary of the region is the solid line that bounds it. Okay? So this is a symbol people usually use for the boundary of a region. Boundary of D. Then the points on C prime intersect the disk itself also form a hyperbolic line. Okay, so like I said, I'm not going to dash out the boundary anymore, but understand that it's not included. But here's our model. And what are a few lines? Well, here's a line. It's a diameter. Here's another line. It's a diameter, so we'll pretend that's the center of the disk. Looks a bit off-center, but anyway. Maybe I should try to draw better circles. All right, so these are all lines. They are diameters. But what else do I have? So those are type 1 lines. Type 2, I take circles that are orthogonal to the boundary. So I just need circles that intersect the boundary here at 90 degrees. And the stuff that's outside the disk I forget about, but the stuff that's inside the disk is part of a hyperbolic line. So, for example, if these are right angles, that's a circle that intersects the boundary orthogonally. Again, just like it was in the upper half plane models, where we have orthogonal circles to the boundary, but I've wrapped the boundary around and it's become the boundary of the disk instead. All right, so yeah, here's one. Here's another example. All right, there's another line, and so on. By the way, one of the exam problems, one of the true or false questions was this. It was if what was it? If two lines are parallel to a third line, then they must be parallel to each other. Right? So in Euclidean geometry, that's obviously true. If I have two lines that are parallel to a third line, they must be parallel to each other. But to see that it's false, you had to sort of think about the upper half plane model that we already talked about. Here I'll just show it in this model. Do I have two lines here that are parallel to a third, but not parallel to each other? How about this? This line and this line are both parallel to this guy, but not parallel to each other. Okay, so just a point of interest. So what do we have to do? This is actually a fairly long section because we have to go ahead now and show that this model satisfies all of our postulates of hyperbolic geometry to show that it's consistent. And we'll do that next time. I'll see you then.